All right. I want to introduce our next speaker, Shlomo from Mellanox, who's going to speak to us about SmartNIC hardware offloads, past, present, and future.
Hello. Rony was not able to attend, so it's just me. So I am going to talk about hardware offloads. Many of the things were discussed in the past day, but it's a good time to recap them maybe. When we think about hardware offloads and data plane in software in general, there we go. So basically, what summarizes the biggest challenge of developing data plane platforms, and I've been dealing with that challenge ever since the inception of NFV way back in 2013, more or less, is you basically have to balance two conflicting requirements, which are flexibility and performance. To achieve flexibility, to get great performance, what you need to do is to optimize your code to do exactly what it needs to do, nothing more, nothing less. But in order to provide flexibility, you're introducing platforms and frameworks that from performance point of view, they're just overheads. Now, OVS is a very flexible platform. It is actually the platform that gave rise to NFV. It is giving us a programmable data plane. It's the first time that applications can basically dictate what the data plane is doing without having some type of vendors in the middle. And the only way to get performance from OVS flexibility is through hardware offloads. Now, there are some numbers and graphs that show the difference in terms of performance when you do hardware offloads. It's between, it can be more than 2 orders of magnitude more in hardware than in software. But I think that the most important point to realize is that this is the way to get line rate. And as network speeds are still doubling every few years, while CPU processing are not anymore, and CPUs are expensive and power hungry, and the only way to, and this was actually was also discussed previously, the only way to get line rate performance is with the hardware offloads. Now, so suppose we do want to integrate hardware offloads. Let's dig in and try to describe how our hardware offloads are integrated into OVS and what needs to be done if someone wants to use these hardware offloads. So hardware offloads, we're basically using SRIOV, which basically SRIOV gives pass-through to the VM, which gives bare metal, which is the mechanism to get bare metal performance. There are two big caveats with SRIOV, which is one, if you are using SRIOV, you need to install the vendor driver in your VM. And the other one is that SRIOV doesn't really natively support live migration. VirtIO basically handles these two caveats in the form that you can install a VirtIO a VirtIO driver in your VM, and it does support native live migration. So in this version, what we're introducing, VDPA is the industry effort to have VirtIO hardware implementations. It is going to be supported in our next Mellanox NIC in the Connectix 60X. It's already supported in Bluefield and in Bluefield 2. But we do need to control this VirtIO, or the hardware, and OVS is the platform to control and to instantiate these devices, and we're introducing a new net device to OVS, which is a VDPA net device, which will basically be able to receive these parameters and control the hardware when you're creating these VirtIO interfaces. Now, until we're going to have VirtIO in hardware, which would take some time, we're also offering a software acceleration for VirtIO. That means that still the embedded hardware switch will do the switching. It will send the packet to a VF device, but then we're introducing a software layer that just basically takes the packets that are on the VF and forwards them to a VirtIO device. So basically, the VirtIO backend is still implemented in software, but the switching is not done in software. So basically, with that, we get the performance that is bound by the memory copy, more or less, restrictions, which is about 7 million packets per second per core. And this work is in the mailing list, and it is something that we have tested with a few customers, and it's really addressing the immediate requirement for VertIO with increased performance. Okay, so let's try to understand what happens when we enable hardware offloads in OVS and how this is done in the control and data planes. So in order to enable hardware offloads in OVS, basically all that needs to be done is just to set the hardware offload configuration in the OVS database, and that's it. Everything is done transparently in the following manner. Basically, once this hardware offload is enabled, every flow, add, delete, and stats event are basically forwarded to a hardware offload thread that tries to offload this flow that was just inserted to the OVS data plane to the hardware. There are two hardware software data planes in OVS. The first is the kernel, and the other one is DPDK. And each one has a different mechanism to offload flows to the hardware. The kernel uses TC, and DPDK uses RTE flow. Let's look at what happens when basically the OVS thread receives the request to offload some flow. So basically, what it takes is it takes this flow that now was added to the OVS data plane, and it either translates it to a TC filter command or to an RTE flow command. TC is the traffic control mechanism in Linux. It's been there for a few decades, I think. One of the components of traffic controller is a packet classifier, and amongst the various packet classifiers that exist in TC, Flower is the one that classifies flows. So basically, what's done is that this OVS flow is translated to a TC command. Which basically and it's just mapping the matches and actions to TC matches and actions. In RTE flow, RTE flow is an API that basically is forwarded to the DPDK PMDs to do the offload themselves. Now, one thing that is important to realize when this hardware offload is enabled and the TC command is installed is that when you look at the kernel pipeline, TC comes before the open vSwitch kernel object. So that means that if a packet goes through TC, and it's the same that would happen in software, because OVS and the TC integration is a very it's a very nice infrastructure that can give us a gradual acceptance of hardware offloads in a way that packets the filters are first translated to TC, and TC is a software implementation. And if the NIC vendor also supports offload, these TC commands can be offloaded to the hardware. So what's important to understand that TC is a software component. So TC being the first component that is processed by the kernel pipeline means that the flow will basically never reach the open vSwitch kernel object. That means that if we have a TC filter command that's just a few matches and then forwards the packets to another point, then basically it has a terminating action which would just forward to the port itself, and the action would end there. This is what we had up till now with all the commands that we were supporting with hardware offload, because all the commands that we were supporting were basically finished with some termination action, such as forward or drop. But this is changing a bit, because when we're starting to introduce offloads of recirculations, especially when we try to offload the connection tracking, what happens is that the filter that we are offloading does not end with a forward or a drop, but rather ends with a go to another chain. So what can happen is that TC can start processing this packet, do some matches, do some actions, but then it would like to continue to do the recirculations and go to another chain. The other chain might not exist in TC for two main reasons. One is that maybe that filter, whatever is happening in that other chain, is not supported by TC because TC has less features than OVS, and we are adding more support as time goes by, but it's still not complete. Or the other option is that all of these flow offloads are not synchronized, and it can happen that the first flow is installed in TC, but the other one is not installed in TC, and it happens that TC cannot continue from where it were. So basically, what we need to introduce is a way for the packet to start continuing in TC and continue its processing in the Open vSwitch. And we need some mechanism in order to so what's important to understand is part of the processing is done in TC and the other part needs to continue in OVS, and we need to communicate to OVS the fact that some of the work was done, and more specifically we have to tell OVS that it should start within a specific recirculation ID. The way to pass this information in the kernel is through SKB, and for this kernel version, for kernel 5.4, we introduced a new TC SKB extension just for this purpose. So if we summarize how everything works in the kernel, so first of all, packets are processed by the Open vSwitch entirely. This can happen either if there's no hardware offloads, or if there is some TC limitation that we didn't that was not implemented yet, that is causing an implementation which would cause the fact that we are not able to offload this to translate an RTE an Open vSwitch flow to a TC command. Packets can be processed either entirely the packet can be processed either in TC in software or in hardware. It will be processed in software if the NIC vendor is not able to or decides that it cannot offload this method, so it will be processed in software, or it is supported, then it can be done in vendor. Packets can be partially processed by TEC and then continue to be processed in Open vSwitch. This can happen if we are implementing recirculations. So if we look in the diagram, it basically shows that if we look in the packet, it can either be entirely processed by hardware, or if the hardware does not support this, so there could be a hardware miss that can then need to restore some state and continue the processing in TC. TC may not be processing the entire packet in software because it probably needs to go to some recirculation. And then there's a TC miss, which will continue which will forward the packet to the Open vSwitch, where it will, where it itself might not have the entire processing, which will need to go to the Open vSwitch user space parameter, but this is as usual. Let's talk a bit about DPDK. Currently, DPDK offloads only support partial offloads, meaning that if you take the master branch in OVS, the only offloads that you get when you're using DPDK is matches offload. Basically, the matches are done in hardware. The hardware sets some type of tag that can be used in software to basically identify the flow that was matched. So basically, the acceleration that is done in DPDK is to accelerate the flow matches. This is a partial offload, and we want to take DPDK forward in the form of full offloads. Full offloads means that now we would also need to implement the filter's actions also in hardware. So this is the work that we've been doing. It's on the mailing list. There's very active discussion about them and just about the basic offload commands that we have submitted on this mailing list, including forward, drop, some rewrites, and encapsulations. But the DPDK offload model is becoming a bit more complicated when we start talking about tunnels. So tunnels, there's the NCAP and DCAP of tunnels. Tunnel encapsulations in DPDK is relatively straightforward because when we work with DPDK, we basically get the encapsulation buffer, and all we need to do is put in a headroom and forward it. But the encapsulation in DPDK is built from 2 steps. The first step is to classify the tunnel, which is, for example, by matching on the UDP port. decapsulating it, and basically there's an implicit recirculation via the form of tunnel pop over a virtual port. And only then we are only basically able to match on the outer and inner headers and do the decapsulation and work over tunnel traffic. Now, when we want to realize this software model in hardware, we are basically now introducing a multi-table architecture in hardware, because up till now we were only able in hardware to do the entire matches and actions in one action, but now it needs to be split to multiple actions, because the first action, the first thing that the hardware needs to be done is to do it. Basically, we're trying to offload the two filter commands. The first is the one that matches on the tunnel type, and then the other one that does the actual matching on the filter itself. So basically, what we need to do is to, because we are running in DPDK, we would need to implement the hardware model in OVS. And the way that we chose to do that is to, once we get the first filter command, which is the filter command that matches on the UDP port, we would offload that to group to the first table, and then we would jump to another table that might not exist until that other filter is being downloaded to hardware. So at this point, we would need to handle misses in software. Misses in software means that we were able to match on the first flow, meaning that we were able to match on, for example, if this is VXLAN, we were able to match at ports 4789. But then the packet came up to software. Now, when the packet came up to software, because it was not able to continue to the next to the brint rules, we need to continue in software in the brint, but we need to somehow also initialize the fact that we already know the vport of this packet. So this is also being used by this mark mechanisms that we're now able to basically communicate some information about some processing that was done in hardware and continue its processing in software. So once we have this mark, we're able to associate this mark to a vport, restore the vport information put on the packet, and then let the software continue the processing. When we realize this hardware model, we also need to change a bit the way that the software is doing things with the way that the hardware is doing things logically, because in the software point of view, once you classify the packet, you can decapsulate the packet and continue. But in hardware, if we were to decapsulate the packet and we would have a miss, and we would go up to software, we would basically see a decapsulated packet and none of the rules would match on it. So basically, when we were translating the hardware model, we would need to move the decap action only after we're able to know that the packet misses will be correctly handled. Things get much more complicated when we start to talk about the connection tracking. Now, this is a bit of a teaser slide, because first of all, it's work still in progress, but connection tracking, the biggest challenge with connection tracking is that it is a multi-step solution by design. You first send the packet to connection tracking. Only once you get that state information, you are able to ask about. You're basically able to match about the city state and make some actions according to that. This is a multi-table model, which is, as we saw before, every time that you move to a new table in hardware and every time that you have new steps, it's possible that you would get hardware misses that would need to be, so some of the processing will be done in hardware and some of this processing will need to be continued in software. So also in hardware, we need to have that state being matched on, and this can be realized through hardware registers. But the mishandling is something that also needs to be handled by the Open vSwitch DPDK, in the fact that it needs to restore either city state or flow state according to whatever was processed in hardware, and then it needs to be that context need to be restored in software before we can continue the processing in OVS. So the main takeaways from this presentation, maybe that I want you to take with you, is that first of all, hardware offload is the way to get high performance in OVS. hardware offloads can work both in SRIOV and in VirtIO. Hardware offloads, but by the fact that hardware offloads are enabled, this does not compromise the system logic. This is by design. It is designed in a way that software is always there. Software is the fallback if something is not implemented in hardware. Something is the fallback if only if it is partially handled in hardware. And the integrity of the software or the integrity of the system, more precisely, will always be preserved even when hardware offloads is enabled, and there are some restrictions with the hardware. Hardware offloads are added, can be added incrementally to OVS. This is due to the fact that it is based on TC or on RTE flows, but TC has a software backend. And if it is not handled in TC, it is handled by OVS. The kernel data path of the hardware offload is handled by TC, and the hardware model itself is implemented by the vendor drivers. But in DPDK, the hardware offload is implemented with RTE flow, and basically the hardware model is implemented by OVS. Thank you. Okay.
Thank you. We have time for a question.
And the flow is offloaded. So I don't have the question as such, but this is the idea. Why don't you compare the packet header, take PF as a source and VF as a destination, and compare it, and whatever the header is changed, just install that flow. This way you don't need TC, you don't need to worry about contract. You can directly, any header, like even if QoS bit change, you can do it on the fly. Is it? It's look. Yeah. No, what I'm. Yeah. So what I'm suggesting, if the IP packet has come, it goes to the OVS, and then it decided this is the output. That's it. What I'm saying is when the packet hits PF and it comes to VM, before delivering to the VM, you just match the header, what the packet actually entered, and after the OVS processing, what is the new header it is. Whatever the change has done, only that you offload to the NIC and then directly send it to the VM. You don't need TC and you don't need contract, and you can do anything because anyways you are doing plain header match. I'm not sure how feasible it is.
All right, let's thank our speaker one more time.